Welcome to the second lecture of EE557 of this week. In the last lecture, we have investigated the stationary covariance property when A is stable in a stochastic system, linear Gaussian stochastic system. Remember, we have proved that we have given a theorem which proves that when A is stable, then sigma infinity exists. Okay? Meaning that sigma k converges to sigma infinity, and the sigma infinity is a finite positive semi-definite covariance. In this lecture, we are going to try to actually prove or give a theorem that gives a stronger result. And that stronger result is going to be the if and only if property. When is it true that we have A is stable if and only if sigma infinity exists? That actually necessitates that we impose additional conditions on our stochastic system. And that additional condition is going to be something called reachability for the stochastic system. Remember that the theorem definitely does not hold in the other direction without any additional conditions, which means that if the sigma infinity can exist even when A is not stable. So that means that the reverse implication does not hold in general. So I cannot say if sigma infinity exists, I cannot say that A is stable. So here we are therefore going to ask for a condition that would make this single-sided implication a double-sided implication, which is an if and only if condition. And that is going to be, the condition is going to be provided by this linear system theory that is given by reachability. So definition, a pair of matrices, these matrices are the A matrix, which is in Rn by n, and an S matrix, which is in Rn by m. Okay, so it can have different number of columns and rows. So S can be a rectangular matrix with n rows, and A is a square matrix with n rows and n columns. Is said to be reachable. If and only if the n by nm matrix, which we define as capital M, we define this matrix M, this is called the reachability matrix, and we put first S into its M rows, M columns, then we put AS, which has again m columns and n rows, and this continues. So maybe I should write a few more columns here. So I have A square S. This continues until A to the n minus first power times S. And the matrix is given like this. It's a partition matrix, and this partition matrix contains n rows, as many rows as A and S, and it has n times m columns. So this is an n by nm matrix. In general, if m is not equal to 1, that means that this matrix is not a square matrix. If m is 1, this matrix is a square matrix. If and only if this matrix has full row rank. Okay? So this is the definition of, this is not the meaning of the reachability, but this is the definition, the condition that is required for A and S to be a reachable pair. So we call a pair of matrices A and S to be, we call these matrices reachable if and only if this matrix has full row rank. Remember that row rank and the column rank of a matrix is equal, and it is called the rank of a matrix. And rank of a matrix is either the number of linearly independent rows or the number of linearly independent columns. So if this matrix has full row rank, then that means that all of its rows are linearly independent. That means that the rank of the matrix is n. Okay? So this is equivalent to rank of the matrix to be n. But since the matrix has n rows, then it is the same as having, the condition is the same as having full row rank. All right? But in general, if m is equal to 1, then this is an n by n matrix. It's a square matrix then. Then having full rank is equivalent to having full column rank, and it's equivalent to being invertible. So I can actually, if m is equal to 1, then m is in Rn by n, then it has having full row rank is equivalent to full column rank, and it is equivalent to actually being invertible. And being invertible is equivalent to determinant of m not equal to 0. Okay? So if you consider m is equal to 1, then determinant m being non-zero is equivalent to the reachability. Okay? But this is the definition of reachability for two matrices A and S. Okay? Now I would like to talk about the meaning of reachability, what this actually means. And in order to be able to talk about the meaning of reachability, I need to define a deterministic system. Xk plus 1 is equal to xk plus suk. Okay? This is my deterministic system, and reachability, the concept of reachability has some specific meaning on that system. Here A is an n by n matrix, and we see therefore xk is in Rn, and S is n by m. That means that uk is in Rm. So this is therefore an m input system with an n-dimensional state. All right? It is in some way related to the controllability of this type of system. What do we mean by controllability? We would like to play with this state vector. Okay? I would like to be able to change the state vector of this deterministic system by playing with u. By choosing different inputs u, I would like to be able to change the state in any way I like. So here, ideally, what I would like to do is to start with an arbitrary initial condition of the system, which is x0. I would like to choose u0, u1, etc. And I would like to bring this initial condition to an arbitrary final condition, xf. Okay? That is the most that I would like from a system. If I work with a system, I want this input to be capable of changing or steering the system from any initial state to any final state that I would like. Okay? That is the meaning of reachability. I call this deterministic system reachable if by playing with the input, by changing the input, by selecting the input in a suitable way, I can bring the system state from any initial state x0 to any final state xf. That is the meaning of a system being reachable. In general, the reachability is only related to these matrices, of course, A and S. And the condition for reachability is this condition. Now we're going to see why actually we would need this condition for this system to be reachable. You might have heard another name for a similar topic that is called controllability. So in control systems, if you take the control course EE557, you would see both of these type of concepts, controllability and reachability. In general, they are different topics and they have different meanings on a system, but if you are only working with continuous time systems, controllability is equivalent to reachability, and of course reachability is equivalent to controllability. That is why this difference is not really important for continuous time systems. But when you go into discrete time systems, the controllability and reachability starts to become quite different from each other, and reachability is the more powerful, the stronger condition there. Okay, and that is what we need here in this course. So I will not talk about the differences between controllability and reachability in this course. So I will only talk about reachability. And if you are wondering about what controllability is, you need to go to the linear system theory courses or textbooks. So here let me give you some examples. So suppose that I have the following system. Xk plus 1 is equal to 1, 0, 5, 0, 0. Or let me say, instead of 0, 5, let me say that this is 2. Okay, Xk plus I have 0, 1, UK. Suppose that this is my discrete time system. Then I will ask you the question, by starting from an arbitrary initial condition, can you go to an arbitrary final condition for this system? In order to be able to understand that, this is a single input system, because you see that S has only one column. That means that UK is a scalar. So this is a single input and two-dimensional system, because state has dimension 2. So in order to be able to understand this, I will write the individual state equations. Xk1, the first element of the state, is xk plus 1 is equal to xk1 here, and I have here no input in the first equation, plus 0. So I really do not have to add any input term into the first equation, because this is 0 here. And I have xk plus 1, 2, is equal to xk2, and actually it is 2xk2 plus uk. Okay? And the question is, starting from an arbitrary initial condition, so x01, x02, if I start an arbitrary initial condition, can I end up by changing the input UK here, by selecting it in a suitable way, can I bring the state of the system to an arbitrary condition, xf1, xf2? Okay? And the answer for this system is going to be no. So suppose that I start at the initial condition, let me say 1 and 2. Okay? So you see that the input affects the second state variable, and the first state variable equation is not really affected by the input. We see that the different elements of the states are governed by different state equations here. So the equations here, the system modes are decoupled from each other. The difference equation for xk1 is not dependent on xk2, and the difference equation for xk2 is not dependent on xk1. Okay? That is why the modes of the system are actually decoupled. And you see here that the first state always remains constant, but the second state can be changed, the dynamics of the second state can be changed by changing the input. So here, the question is, can I select some input sequence such that I start with this initial condition and I can bring the state to the values 3 and 4? The answer to this is going to be no, because you see that whatever I choose the input of the system, the first state is always going to remain constant. Okay? okay? That means that I will never be able to change this value 1 to, from 1 to 3 by selecting any input. That means that this system is not reachable. Is it shown also by this condition? In this case, this M is going to be given as follows. So I have here S is equal to 0, 1, and the matrix A is equal to 1, 2. All right? Then the n is equal to 2, and I continue adding terms here until 1 less than n. So this is going to be S and AS. In the control courses, usually we select B here, but here I do not want to select B because instead of S, we are going to use another matrix here, and that matrix is going to be related to the process noise in that case. So we will actually look in this lecture whether the process noise can control all of the states of this system in some way. That's why we are not going to select this S as B in our stochastic system, but we're going to choose it in a different way. So this is S and AS, and S is 0, 1, and A times S is the second column of this one, 0, 2. So you see that this matrix is definitely not full row rank because the first row is 0. So I cannot have linearly independent rows if I have a 0 row. All right? Or you can look at the determinant in this case because M is equal to 1 and determinant of this thing is 0, so this system is not reachable. So why is that? Because this input U does not excite the first mode of the system. The first state variable is not excited by the input here. That is why this system is not reachable, and we see that the condition for reachability does not hold for this system. So when I teach this topic like that, you might think that the reachability is related to the zeros in this S vector here. So, but then you would be mistaken. So in general, these zeros does not have much has much relation to reachability when we don't have independent components like this. Okay, so there might be non-reachable systems even if all of the elements of this S matrix are actually non-zero. So let me give you an example. Let us say xk plus 1 is equal to, I have 1, 1, and xk plus 1, 1, and I have here uk. Let me check this system. Okay? So in this system, I'm actually going to be looking at the individual equations. xk plus 1, 1 is equal to xk1 plus uk, and xk plus 1, 2 is equal to xk2 plus uk. These are the difference equations determining the state variables. So you see that the state variables, or the modes of the system, are still independent from each other, but they're connected through this common input here. So do you think I can start the system from an arbitrary initial condition, and do you think that by choosing the input uk, I can bring the system to an arbitrary final state by using the input? The answer for this system is not going to be positive either. So this system is not reachable. Why is that? You see that these two difference equations are just the same difference equations. Okay? Their coefficients are the same, just their variables are different. Okay? So if I start the system with the initial condition, so let us say this is x0, by choosing the input u in any way I like, can I bring the system to the final state 1, 2? The answer is going to be no, actually, and the reason for this is that there are two difference equations here, and if I give these two difference equations the same initial condition, you see that they also get the same input. Okay? So if I have two systems with the same coefficients, and if I have also the same input for these systems with the same initial conditions, the response of those systems should be the same. So here, by whatever I choose my input here, I will never be able to bring the state to a value where these variables will actually be different, because the same difference equations, same initial conditions, same inputs would give me the same states here, so that I will never be able to reach the state 2, 3 by choosing any input. So this system is not reachable either. Okay? So here, if I check the reachability condition, then it would be 1, 1, and I would have AS is going to be 1, 1 again. So you see that the rows of the matrix are linearly dependent, or the determinant of the matrix is 0. That means that this M has not full row ranked, and that means that the AS pair is not reachable, and the system is not reachable. Okay? So, as a result, by looking at only this S, the 0 elements of S, you cannot decide on reachability. You need to look at also A here. Okay? So here there are different ways to make these systems reachable. For example, if I choose here, if I give you another system, and that system can be xk plus 1 is equal to 1, 2, 0, 0. And I would have xk plus 1, 1 uk. Then such a system would be actually reachable. Okay? And why is that? Let us look at M. In this case, I would have 1, 1, which is S, and this matrix times S is going to be 1, 2, and this is as usual, if you look at the rows of the matrix, this has full row rank, and that means that this system is reachable. This is not reachable, and this is not reachable. Okay? So here you see that for such a system, I can actually add also a 1 here, which would give me that last system, and that system would be reachable. But here, actually, whatever you choose this vector here, you will not be able to make this system reachable. So because such a system can never be made reachable by using only a single input. You need to add additional inputs to this system to be able to make it actually a reachable system. But these details really are not important. It's only important that you understand the meaning of reachability. Reachability means controlling, or an input controlling all of the modes of the system, or our ability to actually steer the system from any initial condition to any final condition. It's the ability of the input of the system to steer the system from an arbitrary initial condition to an arbitrary final condition. But why is there such a condition for reachability? Let us try to concentrate on this equation. So suppose that I start with an arbitrary initial condition x0, and let me calculate x1. x1 is equal to a times x0 plus s u0. Okay? And I can choose u0 in any way I like to obtain an x1 that I like. And then let me write x2 is, I can write this as a times x1. So it is a square x0 plus as u0 plus I have s u1 here. And I can write x cubed then I can choose U0 and U1 in any way I like to obtain an x2 that I like. X3 is going to be a cube x0, and I have a square s u0 plus a s u1 plus I would have s u actually 2 here. Okay, so you see that if I continue in this manner, I can write the following: xk is going to be a to the k times x0 plus, we have derived such an equality before, I from 0 to k minus 1, then I would have a to the k minus 1 minus I here, then s and ui here. Okay. But now I really do not want to work with this equation in this form. I want to write this summation in a matrix vector multiplication form. Okay? And that is going to be as follows. xk is equal to a to the k x0 plus, I will do the following. So I will write here s, all of these terms here, okay, s, as. So I will get a matrix in that form, s, as, and then I have a square s. It is these matrices here, and then I will continue until a to the k minus 1 times s here, and I will write here the corresponding inputs. S is going to be multiplied by uk minus 1, then uk minus 2, and I will continue until u0. Okay? So here let us remember our aim. Our aim is to start from an arbitrary initial condition, and then go to an arbitrary final condition. Okay? So you see that here, that if I want to go to a arbitrary final condition, I need to be able to cancel this vector, and I need to be able to bring out such an arbitrary final condition. And how can I do that? This is the matrix that is formed out of some columns, and these U's, they're actually acting like coefficients for those columns. I know that I can choose these inputs in any way I like, and by choosing the inputs in any way I like, I am actually taking the linear combination of the columns of such a matrix. Okay? So what we are doing here is that we multiply x0 with a to the k, and then we are generating with the input a linear combination of the columns of this matrix. Okay? So this vector related to the inputs is actually generating a vector in the range space of this matrix. Okay? So by choosing the inputs in different ways, we are actually playing with the coefficients of the columns of this matrix, and we are getting different vectors here in the range space of this matrix. Okay? And what is our aim? Our aim is to be able to obtain an arbitrary final condition here. Okay? And if I want an arbitrary final condition here, that means that I need to be able, by using these input related terms, I need to be able to cancel this initial condition related term and then bring out this final condition that I like by using the input related terms. Okay? So you see that, therefore, our ability to be able to obtain an arbitrary final condition is related to how large the range space of such a matrix can be. if the range space is sufficiently large, then I will be able to bring here an arbitrary final condition by using the input. So how large can the range space of such a matrix be? So here I can think about these matrices S, AS, A square S, and then I can continue. So when is it going to be sufficiently number of columns that I will get possibly the largest range space? So here, the largest range space actually is going to be obtained in the last power here, which is a to the n minus 1s. Okay? Such a matrix is going to have the largest range space possible between such matrices for different k. Why is that? Because a to the n minus 1 is the largest linearly independent power of A that we can obtain in general. Okay? We know that by Cayley-Hamilton theorem, if I add here some terms like a to the ns, then a to the n, it can always be written as a linear combination of these earlier smaller powers. Okay? Therefore, these new columns that I add here will always be linearly dependent with the earlier columns. So as a result, adding here powers of the matrix which are n or higher will not bring us any new linearly independent columns here. Okay? So the largest range space would possibly be obtained at the n minus first power here. Okay? And let me write this as xn here. Xn here is a to the n times x0 plus this matrix S, AS, and I would have a to the n minus 1s, and I would have my inputs un minus 1, un minus 2, going until u0. Okay? Now, in order to be able to have an arbitrary final condition xn here, I need to be able to generate any vector in the state space by choosing these input coefficients. Okay? So in order to be able to have an arbitrary final condition here, the range space of this matrix should be Rn. So this is my matrix M, and the range space of M should be Rn for reachability. Why is that? Because here x0 is arbitrary. As a result, this vector is arbitrary and this vector is arbitrary. In order to be able to obtain two arbitrary vectors here, I need to be able to generate an arbitrary vector here by using these inputs. Okay? And in order to be able to generate any vector in Rn by using these inputs, the range space of this matrix should be Rn. Okay? What it means is that by using the columns of this matrix, I can generate any vector in Rn by choosing suitable coefficients in the inputs. Okay? But so the reachability and if the range space is not Rn, then there will be some arbitrary vector combinations here which I will not be able to satisfy such an equation. Okay? So reachability is achieved if and only if range space of M is Rn. Okay? Range space of that matrix is Rn. But what is this condition, range space of M being Rn? It means that the rank of the matrix should be n. Okay? Rank is the dimension of the range space, and as a result, range space of M being n is equivalent to the condition rank of M being n. Okay? But rank of n, the matrix has n columns, and if it has rank n, then it needs to have full row rank. Sorry, the matrix has n rows, and if the matrix rank is n, then it is full row rank. Okay? So you see that in discrete time, we can, when we look at the formula for xn, we see that reachability condition is directly related to the range space of this matrix, and if the range space covers the whole state space, then we have reachability, and if the range space does not cover the whole state space, then we don't have reachability. That means that we have reachability if and only if range space is the whole state space, meaning that we have reachability if and only if rank is n, we have reachability if and only if the matrix M has full row rank. Okay? So this was the meaning of reachability. Okay, so it is related to the linear system theory. So I will not spend any more time on this, but I will go into an equivalent condition that is going to be useful for us. So let us say lemma. So the pair AS is reachable if and only if the matrix I from 0 to n minus 1, A to the I, S transpose, A to the I transpose is positive definite. So now instead of a rank condition, we are writing a positive definiteness condition. Okay? We have again reachability on one side, but we have double-sided implication here. So this is an equivalent condition to reachability. Okay? We are actually going to be proving this. And proof is not actually difficult. So we have seen in the facts that we presented at the beginning of the asymptotic properties that if I have a matrix A transpose A, then this is an arbitrary A matrix, it doesn't have to be a square matrix, is positive definite if and only if A has full column rank. This is for any A in, let us say, N1, N2. We have seen and proven such a property. So a matrix in this form is positive definite if and only if A has full column rank. We have seen an alternative version here, and that version was A transpose is positive definite if and only if A transpose has full column rank, but A transpose having full column rank means A having full row rank for all A in R, N1, N2. Okay? So if I have a matrix of the form A times A transpose, then that matrix is positive definite if and only if the matrix A has full row rank. Okay? So now let us look at this matrix. M times M transpose. M is S, AS, A square S, going until A to the n minus 1 S, okay? Times M transpose. And M transpose is going to be everything transposed here. So I have S transpose, and S transpose A transposed, and S transpose A square transpose. This is going to continue until S transpose A to the n minus 1 transpose. Okay? And using the partition matrix multiplication rules, I can actually show that this summation is given as follows. S times S transpose, this times this, plus AS S transpose A transpose, this times this, plus A square AS S transpose A square transpose. This continues until A to the n minus 1 times S transpose A to the n minus 1 transpose. Okay? But you see that this is nothing but this matrix. This is I from 0 to n minus 1, A to the I, S transpose A to the I transpose. Okay? So you see that this matrix is M times M transpose. Okay? And as a result, by using the above result, this matrix is positive definite if and only if M has full row rank. But it is the definition of reachability. Okay? So this matrix, I from 0 to n minus 1, A to the I, S transpose, A to the I transpose. So this is positive definite if and only if M has full row rank. Okay? But M has full row rank is equivalent to AS is reachable. Okay. So that completes the proof of the lemma. So now I'm going to give an additional lemma here. I will have a lemma and a corollary actually. The lemma is as follows. I from 0 to n minus 1, A to the I, S transpose, A to the I transpose is positive definite if and only if I from 0 to L, A to the I, S transpose, A to the I transpose is positive definite for, let me write it here, for all L greater than or equal to n minus 1. So here we see this matrix, and this matrix is summed from 0 to n minus 1. Okay? Here we are said that this is the summation is from I to L, and L is larger than or equal to n minus 1. Okay? So if I sum here some additional terms, that matrix is also going to be positive definite. And furthermore, when I sum more terms, if the resulting matrix is positive definite, this sum should be positive definite. The sum with the less terms will be positive definite as well. Okay? The proof is not really difficult actually, by considering the Cayley-Hamilton theorem. I will not be able to explain the Cayley-Hamilton theorem in this course. You need to go to, if you don't know about it, you need to go to course 501 and repeat those topics. So if I have the matrix S, AS, and A to the n minus 1s, I have talked about the fact that adding additional columns here will not change the rank of this matrix. Okay? So the rank of this thing is actually equal to, I will have this, it is the rank of the following matrix, S, AS, A to the n minus 1s, A to the n s, and I can continue until A to the ls. Okay? The ranks are equal. Why is that? It is just because of the Cayley-Hamilton theorem. Cayley-Hamilton theorem tells us that any power of A which is larger than or equal to the size of the matrix n, so A to the n plus 1, A to the n plus 2, can be written in terms of the lower powers of A to the 0, which is the identity matrix, A to the n minus 1, etc. Okay? So A to the ns, the columns here, can be written as a linear combination of the earlier columns. Okay? So here, these new columns that I add to this matrix, they cannot increase the rank. The rank the rank would always remain the same when I add these additional columns here. That means that the rank of this matrix would always be equal to the rank of this matrix. Okay? As a result, if the matrix S, AS, A to the n minus 1s has full row rank, then this is going to have full row rank. If and only if, this is not if and only if this larger matrix has full row rank. A to the ls has full row rank. Okay? But you see that this matrix times its transpose is this matrix, and this matrix times its transpose is this matrix. That means that this matrix is positive definite, which is equivalent to the condition of this matrix having full row rank, is if and only if this matrix is positive definite, which is equivalent to the condition of this matrix having full row rank. Okay? So that would actually complete the proof. So I have a corollary of this lemma, and it is quite easy. So here, if this result is true for any L which is larger than n minus 1, I can let L go to infinity. Okay? I can of course let L go to infinity. So if this summation exists, I from 0 to infinity, A to the I, S transpose A to the I transpose exists, then I can actually give my result, I from 0 to infinity, A to the I, S transpose A to the I transpose is positive definite, if and only if this I from 0 to n minus 1, A to the I, S transpose A to the I transpose is positive definite. And the proof is trivial. Use the lemma and let L go to infinity in the lemma. Okay? So now we are almost about to go to our theorem, but before that I will have some facts that I need to talk about linear algebra. Okay? So what did we learn so far? We learned that we have a condition on the linear system that is called reachability. And reachability is related to the ability of the input of a system to steer the system from an arbitrary initial condition to an arbitrary final condition. And the condition for reachability is about a matrix having full row rank. That matrix is called, M is called the reachability matrix. If the reachability matrix has full row rank, then we have reachability. If the system is, or if the matrices are reachable, then we have the M matrix having full row rank. And then we have seen an equivalent condition. And the equivalent condition is A and S, that pair is reachable if and only if this matrix is positive definite. Okay? And we have also seen another equivalent condition, and it is this matrix being positive definite. All right? So now let us talk about some facts about linear algebra. That is going to be useful in the proof of our theorem. The first thing that I'm going to say is that the matrices A and A transpose have the same eigenvalues. Our A matrix is a real valued matrix, and we have its transpose. We have a fact, and that fact tells us that A and A transpose, they have the same eigenvalues. Okay? How can I be sure about this? So, if I calculate the characteristic polynomial of A, then it would be determinant Si minus A. Okay? In general, a determinant of a matrix is the same when I take its transpose. So, if I have two matrices, one is the other's transpose, then their determinants are equal. So that means that this is determinant of Si minus A transpose. Okay? So the transpose does not change the determinant. It's one of the properties of determinant. And that is equal to determinant, the matrix Si, its transpose is itself, minus A transpose. Okay? And you see that this is nothing but the characteristic polynomial of the matrix A transpose. Okay? So if lambda I is an eigenvalue of A, if lambda I is an eigenvalue of A, then it's the root of the characteristic polynomial of A. This is true if and only if, because these polynomials, characteristic polynomials, are equal, if and only if it's an eigenvalue of A transpose. Okay? So if the matrix A has an eigenvalue lambda I, then the matrix A transpose has an eigenvalue lambda I. All right? What about the eigenvectors? So of course, the matrix, if it has an eigenvalue lambda I, then it has an eigenvector, at least one eigenvector corresponding to that eigenvalue. And the matrix A transpose has also the eigenvalue lambda I. Then what about its eigenvector? Then it has also at least one eigenvector corresponding to that eigenvalue. So I can here say the following. The eigenvectors of A transpose are the left eigenvectors of A. What do we mean by this? In general, we have the eigenvector eigenvalue equation given like this, okay? And what we consider in all of the other courses is this type of eigenvectors. And you see that this eigenvector multiplies A from the right. So these regular eigenvectors, EI is a right eigenvector for eigenvalue lambda I, okay? In general, we don't write the right eigenvector if the meaning is already evident, but in general, we call this EI, when there is confusion, we call this I to be a right eigenvector of A, okay? So if this equation is satisfied, then lambda I is actually an eigenvalue of A. That means that the matrix A transpose has also an eigenvalue at lambda I. And the eigenvector for lambda I of A transpose can be different than this EI, okay? So I will call this eigenvector Li here, okay? And this is this eigenvector of A transpose belonging to the eigenvalue lambda I is Li. That means that Li is a right eigenvector of A transpose for lambda I. The earlier one is an eigenvector of A for lambda I. Okay? Now this equation looks fine, but I would like to write this equation in terms of A. So I will take the transpose of both sides. Li transpose A is equal to lambda I is just a scalar Li transpose. Okay? When I have an equation for the matrix A like this, you see that this vector multiplies A from the left. And the vector just satisfies an eigenvalue, eigenvector type of equation. In this case, I have a horizontal vector here times A is equal to a scalar lambda I times an horizontal vector. Okay? And if such an equation is satisfied, and it is definitely satisfied because you see that when I take the transpose, I get this type of vector. I call Li is a left eigenvector of A for lambda I. Okay? So we see that eigenvectors, right eigenvectors of A transpose belonging to the eigenvalue lambda I, they are called left eigenvectors for A belonging to lambda I again. Okay? That is something that I need to mention. The concept of a left eigenvector. So eigenvectors of right eigenvectors of A transpose, they are left eigenvectors of A. All right? And the final fact that I'm going to mention is the following. So, since A is real, if lambda I is complex, if lambda I is a complex eigenvalue of A, then lambda I complex conjugate is also an eigenvalue of A. Why is that? Because if A is real, then the characteristic polynomial has real coefficients. And if a polynomial has real coefficients, and if it has a complex root, then complex conjugate of that root should also be a root. Okay? And therefore, if A has a complex eigenvalue, its complex conjugate should also be an eigenvalue. What about the corresponding eigenvector? I know that A times EI is lambda I times EI. So EI is the eigenvector belonging of A, belonging to lambda I. What about the eigenvector for actually lambda I complex conjugate? In order to be able to find that eigenvector, I will take the complex conjugate of both sides. So if I take the complex conjugate of both sides, then I see the following. In general, A is real, so it gets outside the complex conjugate, and I have EI complex conjugate, and I can actually distribute the complex conjugate operation over the complex multiplication here. So this is lambda I conjugate, EI conjugate. So we see that the eigenvector belonging to the complex conjugate of the eigenvalue is the complex conjugate of the eigenvector belonging to the original eigenvalue. Okay? So that is, so for lambda I, if I have EI as the eigenvector, then for lambda I conjugate, I have EI conjugate as the corresponding eigenvector. Okay? I can do the same thing for the eigenvectors of A transpose. So I can, if I have complex eigenvalue for A transpose, then I can have the complex conjugate of the same eigenvalue as another eigenvalue, and the complex conjugate of the eigenvector becomes the eigenvector belonging to the complex conjugate eigenvalue. Similarly, I can do the same operation for the left eigenvector, Li. So now I'm going to take the complex conjugate of this equation. So when I take the complex conjugate of Li transpose A is real, it can get outside of the complex conjugate operation. And Li transpose, if I take its complex conjugate, it's going to give me the Hermitian of Li. Okay? So if I have Li transpose A is equal to lambda I Li, if I take the complex conjugate of both sides, this is going to give me Li Hermitian. This is transpose still. Li Hermitian A is equal to lambda I complex conjugate Li Hermitian. Okay? So now with these facts, we are actually ready to actually write our theorem. Okay? Define a square root S of the matrix GQG transpose as S times S transpose is equal to GQG transpose. Okay? So here we are defining a square root S of the matrix GQG transpose, and that S matrix is defined as the matrix which satisfies this equation. Okay? S times S transpose should be GQG transpose. We can always find such a square root for any matrix, any positive semi-definite matrix. Okay? We define the matrix S with this equation. Then the statement of the theorem tells us the following. If AS is reachable, then A is stable if and only if sigma k converges. Or I can write here, sigma infinity exists. Let me write here, sigma infinity exists. Or sigma k convergence. It means the same thing. So here our theorem tells us the following. I first find a matrix S that would satisfy this equation. Okay? This can always be done for any positive semi-definite matrix given as GQ transpose. And the theorem statement tells us the following. If this pair AS is reachable, then there is an if and only if relationship between the existence of sigma infinity and the stability of A. Okay? So this was our aim. We were going to enforce an additional condition on our system, and that is this reachability condition. This matrix S defined as the square root of GQ transpose. If this S and A, if this pair is reachable, then we can say that when sigma infinity exists, A should be stable. Okay? So there is a double implication in this case. All right? In the next and the final lecture of this week, we're going to be working on this theorem, and we're going to try to prove it, and then we're going to try to give some meaning to that theorem. But that's all for this second lecture. Thanks for watching.